So in my last video, we covered the subject data structures in which we studied red-black tree. So now, today we'll be starting with theory of computation. In theory of computation, we have not covered NFA and DFA, but I'll be giving a short recap on what is NFA and DFA, and then we'll starting with regular expression. So regular expression is basically made from language. A language is a set of strings, a combination of A, B, where symbols is represented by the summation sign. A, B, A, and so on. So like this is known as language. And a set of languages is represented by what is known as grammar. So this will be covered in our later classes. So first, for now, what is NFA and what is DFA? Let's cover that. NFA and DFA are representations of regular expressions or some statement. Let's assume we have A asterisk, A plus. Let's understand this. A asterisk means you can have any combinations of A and there can be zero number of A's also. And single A means only a single occurrence of A is allowed. A plus means that you can not have an empty string. Empty strings means zero is not possible. So 1A, 2A, and so on. So this is what is A asterisk. This is known as clean closure. And this is your string. So now let's go on. So now what is NFA and what is DFA? We'll cover it in one slide using a differentiating table. NFA is that when you draw an automata, suppose this is your initial state is represented with the arrow at the start, and your final state can be represented by QF or Q1 depending on what you want to write. So now let's say on getting a single A, we can go to QF. So we'll write A. Now if I say A plus B, that means A can also come or B can come and you should reach the final state. If you accept that string, you should have a double enclosed circle at that place. A plus B, that means A and B will also go here and then only your string will be accepted. Suppose your string is A, it is accepted. B, then it is also accepted. But is an empty string accepted? No. Why? Because A plus B asterisk will do that. But this is not an NFA. NFA means that you have more than one representation. Like A is also going from Q0 to itself and also going forward. That means we have two representations of the same symbol. Now in case of a DFA, you should have only one representation of a symbol going from one state to other. Suppose this A goes from Q0 to QF and B comes back on Q0. So you have one representation of A here, one representation of B on Q0. So AB covered here. In QF, we have a representation of B going this side, but we don't have a representation of A. Now this will be a DFA. In DFA, if we don't have any, suppose self loop means any number of A's can be accepted. Suppose if we don't have any other string and we don't want to accept those having A at the end, what we do is a dead state. A dead state means that it will go into an infinite loop, what we call in a coding language. So infinite loop means it will never come out because it will not be accepted. So this is basically what is NFA and DFA. So next. So now regular expression. Regular expression is a method to represent a set of strings or a language. Let's say, for example, I write A asterisk. We covered that right now. So it will be an empty string, a single A, a double A, or any number of A's. Now, if I have A asterisk, that means a single string, 2 times A. Now, this can repeat itself. So, 2 into 2, 4 times A, then 2, 2, 2. So, 2, 4, 6 times A, and similarly, so on. So, now let's try to make the automata to get familiar with regular expressions. So, for a single A asterisk, what we do is we have a single Q naught. Now we can add a self loop here because if epsilon is accepted, that means nothing is also accepted. An empty string, what we call. So we have to place a self loop of a single A. So empty string accepted, single A accepted, double A accepted, and so on. Now when we have A asterisk, that means only if our A occurs in multiple of 2 or an empty string, it will be accepted. So here, first A goes on the next state, then it comes back on the same state. So Q0, Q1. It should be accepted only when either it's an empty string, epsilon. You start here, you end here. Or when you have a single A, you move here. When you have the second A, you move here. And this is our automata. So let's erase this to avoid any confusion. So this will be a final automata. So now let's see some more examples based on them. So let's say now we have A plus, let's take another example. R is equal to x plus y plus zx. So that means empty string will also be accepted here. That means your initial state will be your final state. Now x, y, z all will be accepted. So can we write it like this? This will be a wrong answer. Why? Because this means that we should have an x, we should also have an y, and we should also have a z. But we have a plus sign. Plus means x, y, z, any of them. So what we'll do is we'll place self loop of each of them, either like this x, y, z, or q naught, one of x, then second of y, and then third of z. So this is our first representation of a regular expression. Now let's move on to regular expression identities by which we'll have a better understanding on them. So identities. So a first identity says that one regular expression plus second regular expression is equal to a second regular expression plus first. Now, when you have A into B, it will not be equal to B into A. That means first occurrence of A and first occurrence of B is not the same thing. That is R1 dot R2 is not equal to R2 dot R1. Next property, R1 plus R2 plus R3 will be R1 equal to R1 plus R2 plus R3. Now, next identity, fourth one is R1 into R2 into R3 will be R1 into R2 into R3. These will be equal. When we'll take on some examples, it will be more clear. So then after that, we have if R is 5, what can we say about the language of R? 5 means there's nothing there on an empty set. That means your language is not representing anything. It's just an empty thing. If you have epsilon, that is an empty string. This is a null set. This is an empty string. The difference is clear. This is a null set. This is an empty string. So now, language of an empty string is itself an empty string. Then we can say Then R into epsilon is equal to R is equal to epsilon into R. 7. Seventh identity we'll do is R into R is equal to R square. That is, let's take an example. A into A is similar to A square. Next, R plus R is equal to R. That means either we can have A plus A means either we can have A or we can have A. That's the same thing. We should have A ultimately. Next property, we have epsilon plus R dash is equal to R dash. This will be a very useful property. We'll see in our examples. Then after that, we have phi. Null set clean closure will give us an empty string. This is important. An empty string clean closure will give us again an empty string. Then if we say phi into epsilon is equal to epsilon into phi, this will be equal to phi. Now assume phi to be 0 and then try to remember this, because sometimes you may get confused. So 0 into anything is equal to anything into 0 is equal to 0. 0 is basically phi. So 12th identity. If you take the clean closure of R and then again take a clean closure, you still get the clean closure of R. 13th identity. R clean closure into R is equal to R into R clean closure. Next, we have 14th. I'll try to write it here only. So P into QP asterisk will be equal to PQ asterisk into P. Now, the 14th one is an important identity. We'll see that on the next page. 14th. It says R asterisk plus S asterisk whole asterisk is equal to R asterisk S asterisk whole asterisk is equal to R plus S asterisk. How? Let's see. So now R asterisk S asterisk, that means you can empty string here, and whole is also an empty, taking an empty string. That means if this is an empty string, this can be there. If this is not an empty string, this can be there. Let's suppose A asterisk plus B asterisk whole asterisk. We can have A, we can have B, we can have epsilon. If I write A asterisk, B asterisk, whole asterisk. Can I have here A epsilon here? Yes, we can have epsilon here. Can we have A here? Yes. Can I have B here? Yes. If I write A plus B asterisk, can I have epsilon here? Yes. Can I have A? Can I have B? So as we can see, all three cases satisfy this condition. Now we have done with our identities. Now let's start with making some regular expressions into finite automata. So the first question is, you have to convert this finite automata into a regular expression. So A, let's first draw it. C, A, and B comes back and self loop of A. Now here, as we can see, what does this part mean? This part means A asterisk, that you can also have an empty string. Now B, it accepts B. Now B, this you can assume this as a single entity and take it here. So you have a B plus. Now I'll tell you why we are not writing the clean closure here. So then we accept A, then we accept the self loop of A, that is A asterisk, and then B comes back here on the final state. So B. Now B, why did we not write asterisk? We have to write pole asterisk because if we have A asterisk B, like AB, so A, then B, it will be accepted. So this part can also be an epsilon or an empty string. So now, if R is equal to this, so we can write it as A asterisk B, A asterisk B asterisk, using our identity. How? Let's see. You take B common out, B epsilon plus A asterisk. Now we had a property epsilon plus R star gives R star. I'll write that epsilon plus R star is equal to R star. So by this property we get this, and so our answer will be, now R into R star gives us R plus. R plus means empty string will not be accepted. So A asterisk B plus. So I'll erase this extra part. So this is our answer. Now, our final question for today's lecture will be a little tricky. So R is equal to 0 plus 1 asterisk, 0, 0 plus 1, 1, 0 plus 1 asterisk. That means it can accept either 0 or 1 or an empty string, either 0 or 1 or an empty string, but here it should have two zeros or two ones to get to the final state. This is important because this does not have a clean closure. So now, first of all, we should know what is epsilon rules. If for someone who doesn't know, he can say. Epsilon moves means without any string also, we can move from one state to other. Suppose I have A. Now I want to reach Q2, but I don't want any string to reach to Q2. I want to directly reach to Q2. So I'll add epsilon. Epsilon helps us in reaching. Now, by this example, I'll show you what is the necessity of using epsilon here. So in this example, we don't require 0 and 1 as plus 1 asterisk. It is not a necessary thing. It can be an empty string also. So here we'll use epsilon. See, this will be Q naught. Then after that, we don't want any string, but you still go to Q1. Then I'll have a self loop of 0 and 1. So either 0 can come or 1 can come, or an empty string. If it's an empty string, it will still reach Q1. And after that, I want you without any string also to reach to Q2. Now, important, 0. I can't have a same path for 0, 0 and 1, 1. So I separate it. 0, 0, 1, 1. So this will be Q3, Q4, Q5. Then after that, I don't want any string, but I still want to reach Q6, where I'll either 0 or 1. Then without any string, I will reach to my final state, Q7, wherein I don't want self loop. So this will be our answer. Let's see how is this the answer. Suppose I have 0, 0. So automatically here, 0, 0. Automatically here, automatically reaches the final state. 1, 1. So reaches here, 1, 1, and reaches to the final state. 1, 0, 0, 1. 1, 0, 0, 1, and to the final state. So this will be a final answer. If you have any doubts, feel free to reach out in the comment section. So thank you all. Hope you have a great day. If you like the video, do like, share, subscribe. Thank you. In the next lecture, we'll be studying about pumping lemma and others to prove languages. We'll be studying regular grammar and how more complex regular expressions are made. And we'll also study Arden's theorem to write regular expressions using equations of different states. That we'll do in our next class. Thank you.